Obviously, it's never good to drop optical components like that. But in the end, our design or the design of our components, it's much more robust and withstands much higher acceleration forces. If you want to find out how we make sure that our design is okay, stick around and we'll find out. Of course, such a cardboard box can absorb a lot of energy from the fallen component. But in the end, it's not that big deal because our components are designed according to Telcordia. This means they have to withstand much higher acceleration. Why is this important? Yeah, if we take a closer look to the components, you can see all the precisely machined parts and they are aligned very accurately. This means if there is a force due to the acceleration which harms the alignment, the component does not work properly anymore. If I'm talking about higher accelerations, I'm talking about 1500 G. This is a large number, a really big number, and in the beginning, honestly speaking, I did not know what this means. Just to put it into relation for you, for example, a fighter pilot feels the force or the acceleration of up to 10 G in extreme situations. And untrained persons, as we are, can withstand around about 4 G before passing out. The acceleration is one point, the direction of the acceleration is a second point. And if we take a closer look to the left side here, you can see there are 6 directions and we have to test all the 6 directions. Why is this important? If we take this example on the right side here, there are 2 parts which are glued together and the arrow indicates the direction of the acceleration, and obviously this is not too critical. But if we turn this setup by 90 degrees, it's the second sketch here, it is obvious that the acceleration is much more critical than in the first case. So now, how do we qualify our components or our setup for that? We have a mechanical shock tester where we can put in the components, and upfront and after the test, we do an optical or optoelectronic measurement. And the deviation between the 2 measurements must not exceed 0.5 dB. Then we are sure the setup is stable and okay. Okay, now let's go down to the workshop. Okay, now we are down in the workshop and what you can see here is our mechanical shock tester. It's a self-designed machine, and to basically explain how it works, we have this mounting plate here. On top of the mounting plate, we can put our components we want to test. In this case, it's a ROSA, and it's important that you have the possibility to use all 6 directions. Then we have this acceleration sensor, which is connected to the oscilloscope. So it records the acceleration over time. It's important to make sure that we have the right profile for that. And the rest, basically, it's a spring-loaded lever to provide the energy for this test. Okay, first let's take on the safety goggles. And yeah, let's go. Okay, that's the test. It may not look very spectacular, but please keep in mind, those are 1500 G. After the test, we do an optical or optoelectronic measurement to make sure that there is no degradation during this test. Okay, I hope you learned something today. If so, please leave a comment or consider following us, and see you in one of the next videos.